So here's another conservation of energy question. We have four 1 gram spheres. They all have identical charge, and initially they're on a square with side length of 1 centimeter. They're allowed to move away from each other. So first they're held in place and then we let them go. What's the speed when they get very far apart? So let's think about the behavior. They're all repelled by each other, so they're all going to move directly away from each other. Let's just do a new sketch where we get some information written down. So there's a plus, there's a plus, there's a plus, and there's a plus. I'm going to label my charges 1, 2, 3, and 4. 1, 2, 3, and 4. So when we let them go, they're going to start to move away from each other. So move off in this direction. Initially, they're not moving at all, but then they start to move. They're on a 1 centimeter squared, so this side length here is 1 centimeter. And they all have exactly the same charge. So I'm going to write down that Q1 equals Q2 equals Q3 equals Q4 equals our charge Q, which is 10 nanocoulombs. Okay, so let's write down our expression for conservation of energy. And that says that our initial or our final mechanical energy is our initial mechanical energy plus any work done by non-conservative forces. We don't have any friction or anything like that, so the work done is going to be 0. Our initial energy is going to be kinetic plus potential, so let's write that down. So E initial equals initial kinetic plus initial potential. So electric potential energy. Let's do kinetic energy first. So our initial kinetic energy is the kinetic energy of each of these four all added up. They're released, which means they start at rest. So our kinetic energy would be the sum of each individual kinetic energy. So the sum of each 1/2 m times v squared equals 0 because they were released from rest. Okay, so while we're here, let's also write down that the masses of each of them, m1 equals m2 equals m3 equals m4, and we're going to call all of those m, and that m is equal to 1 gram, or 1 times 10 to the minus 3 kilograms. Okay, what about our initial electric potential energy? This one is going to be a bit more work. So potential energy due to a single charge, let's write that down over here. So due to any two charges, it's K times Q1 times Q2 divided by the distance between charges 1 and 2. If you have a system of charges, you have to add up the potential energy due to each interaction. So 1 and 2 will have a potential energy. One and 3 will have a potential energy. 1 and 4 will have a potential energy. Okay, 2 and 3 will have a potential energy. 2 and 4 will have a potential energy. And 3 and 4 will have a potential energy. Okay, so to get our total potential energy, we have to add up the interaction due to every single pair of charge. Let's get to work writing down each of these potential energies. So U12 is equal to K times charge 1 times charge 2 divided by the distance between 1 and 2. The distance between 1 and 2 is the side length of the square, so R12. I'm going to call the side length of the square D. We know that D equals 1 centimeter. We remember that all of our charges are equal. Q1 equals Q2 equals Q3 equals Q4. I'm just going to call them all Q. So K times Q1 times Q2 is K times Q squared. The distance between 1 and 2 I labeled on my diagram as D, the side length of the square. All right, this first one done. Now let's do the next one. U13. So that's the potential energy between 1 and 3. That's going to be equal to K times Q1 times Q3 divided by the distance between 1 and 3. Here's our distance R13. That's also equal to D. So I've got K times Q squared divided by D. Next is between 1 and 4. U14 is K times Q1 times Q4 divided by R14. Distance between 1 and 4 is from here to here. Got to do a little tiny bit of work to find R14. You might notice that R14, this distance, is the diagonal of our square. This makes a right angle triangle. So R14 is a hypotenuse where the two legs are D and D. So R14 equals the square root of D squared plus D squared equals root 2D. Okay, so my U14 is K times Q squared over root 2 times D. If you were a numbers kind of person, you could be putting in your numbers at every single step. I'm going to go for symbols because I just find that a little bit simpler to deal with. Okay, let's do 2 and 3 next. That's the energy between these two. I'm going to switch colors. U23 equals K times Q2 times Q3 times R23. I'm switching colors so that I can put R23 in my diagram. R23 is the same as R14. It's the diagonal of the square. Q2 and Q3 are both Q, so I've got K times Q squared over root 2D. Okay, 2 more to go. U24. U24 equals K Q2 Q4 divided by R24. R24 is this distance, that's equal to D because it's the side edge of a square, so I've got K times Q squared divided by D. Last one is U34, which is K times Q3 times Q4 divided by R34. R34 is our distance between 3 and 4. That's also equal to D. So I've got K times Q squared divided by D. Okay, I've got all my potential energy terms written down. Next, to find the total potential energy, I just add them all up. Let's take the sum now to find our total initial electric potential energy. So I've got U12, which is KQ squared over D, plus U13, KQ squared over D, plus U14, KQ squared over root 2D, plus U23, which is KQ squared over root 2D, plus U24, which is KQ squared over D, and U34, which is KQ squared over D. So my total initial mechanical energy is my initial kinetic plus my initial potential. Oh, actually, maybe I can just simplify this a little first before I write down my final expression. So I can haul my KQ squared over D outside, and I'm left with 1 plus 1 plus 1 over root 2 plus 1 over root 2 plus 1 plus 1 equals KQ squared over D. Outside of 1 plus 1 plus 1 plus 1 is 4. 1 over root 2 plus 1 over root 2 is 2 over root 2. So there's my total initial potential energy. If you wanted to now, by all means, go ahead and put your numbers in. I'm still going to stick with my symbols for a while. So my total initial mechanical energy is my initial kinetic plus my initial potential. So 0 plus K times Q squared over D times 4 plus 2 over root 2. There's my total initial energy. Next, let's write down the final energy. For my final mechanical energy, that's equal to my final kinetic plus my final electric potential energy. Okay, let's deal with the electric final potential energy first. So we remember that potential energy, UE, is K times Q1 times Q2 divided by the distance between 1 and 2. In the final case, the charges are very far apart. Very far apart means R is very, very big. It's approaching infinity. That means that our final electric potential energy is about equal to 0. So when we divide KQ1, Q2 by a very big number, we're going to get a final energy of 0. Okay, so our UF is 0. What about our KF? So our final kinetic energy is 1/2 times M1 times V final 1 squared plus 1/2 M2 V final 2 squared plus 1/2 m3 v final 3 squared plus 1/2 m4 v final 4 squared. Remember we said that all of those masses were the same. We're going to call all of those m. Due to the symmetry of the problem, same mass, same charge, same orientation, all of those final velocities have to be the same too. So VF1 is the same as VF2, is the same as VF3, is the same as VF4. So what I've got here in my expression for my final kinetic energy is 1/2 mv squared plus 1/2 mv squared plus 1/2 mv squared plus 1/2 mv squared. Add them all up, we get 2 times m times v squared. Okay, I think we're ready to put it together. We know our initial potential energy. Our final energy is going to be K final, which is 2mvf squared, plus our final potential energy, which is 0. So we can set those guys equal. We should be able to find the speed. So we say EF equals EI plus work done by non-conservative forces. That means friction and things. That's equal to 0. We'll fill in our EF. That was just kinetic because we're so far apart, there's no potential. So 2 times m times VF squared equals our initial mechanical energy. That's all potential because initially they're at rest. You add up the interactions due to every pair of charge, and what you get is kq squared over d divided by 4 plus 2 over root 2. We're trying to solve for our velocity. So our VF is going to be k times q squared over 2 times m times d times 4 plus 2 over root 2. Then we have to take the square root of the whole thing. The numbers we're going to plug in are k equals 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Q is your 10 nanocoulombs, 10 times 10 to the minus 9 coulombs. M is 1 gram, 1 times 10 to the minus 3 kilograms. D is the side edge length of that square, 1 centimeter, or 1 times 10 to the minus 2 meters. I think that's all of our numbers there. Put all those through the calculator, and what you should get for your final speed is 0.493 meters per second.